So welcome all to 6th tutorial for the course Basic Linear Algebra taught by Professor Inder Kumar Rana. I am Pintu Kumar. I am a PhD scholar at IUR Bombay. Today I plan to cover topics of inner product space. I'll talk something about norms and how are they induced from inner product space. I'll also try to define norm independently and see relation between inner product space and norm space. And I'll talk briefly about something like how do you define norm on a matrix, and then I'll go for Gram-Schmidt's optimization process. Okay, so this is my plan for today. Okay, so I'll begin with defining what we mean by inner product space. Okay, so first of all, let's see like what is the idea behind inner product. So inner product is nothing but a generalization of dot product. So in your school you might have learned that, like, for example, let's say you have 1 comma 2 and you want to take its dot product with 2 comma 3, then what you do 1 into 2 plus 2 into 3 and so on. So this is a dot product, right? So using dot product you can obtain angle between two vectors. Let's say this is v1 and v2. Then you know that v1 dot v2 is given by length of v1 into length of v2 cos theta, right? So using this you can just take this thing on the left hand side is equal to cos theta and obtain value of theta from here. So cos product, this dot product, give you a notation of angle between any two vectors. Okay, so when we extend our notation of everything like vectors or let's say vector transformation or linear transformation, we want a generalized notation for dot product also. Okay, so in mathematics generally when you try to make a concept more abstract or more generalized, you pick some of the properties of your objects that you know and make that as a definition. Okay, so similar thing will happen over here. So we know some of the properties of this dot product and we'll make those properties as definition for any arbitrary thing to be a inner product space. So inner product is nothing but a generalization of dot product. So inner product help you with a notion of angle between two objects. Okay, so now to define what an inner product is. So inner product is a function from vector cross vector, so vector space cross vector space. So it will take input two vectors and returns you with a scalar from the field on which this vector space is defined. Okay, so these things should satisfy these four properties. Okay, first property is if you take inner product of x plus y with z, then it is same as taking inner product of x with z plus inner product of y with z. So this is linearity property. So with respect to the first component, it's sort of linear. Again, if you take c of x and you take its inner product with y, then your c comes out. Okay, so this is the second property. Third property is if you inverse the notion, like if you take the dot product between x and y or y and x, then it is nothing but equal to the complex conjugate. So the symbol on the top is something called as complex conjugate. So you might know, like if you have a number like x plus iota y, then its complex conjugate is given as x minus iota y. So if your field, let's say over here, is just real number, then this property will become that x comma y is nothing but y comma x, because for real number x is equal to x for all x belonging to real number, because you don't have any complex component, so that thing will remain same. And the fourth property is that the inner product of a vector with itself is always greater than equal to 0 till the time x is not equal to 0. If x is 0, then it will be 0. Okay, so there are four properties that we should look to check whether something is an inner product or not. First is that it should be these two things mean that it is linear with respect to first component, that is x plus y will split and c will also come out. The third property is that like if you reverse the role, then the inner product is just the complex conjugate of each other. And third is that the inner product should always be greater than equal to 0. Okay. So let's look at an example. We'll try to verify all the 4 properties for this one. And this is something called as the standard inner product on Fn. So you can replace Fn by Rn, so then it would become a standard inner product on Rn. Okay. So if you look at the definition, how it is defined. So let's say your x is given by a1, a2 till an, and b is also given as b1, b2, bn. Then x, y is nothing but summation I is equal to 1 to n ai into bi conjugate. So if you compare it to your dot product, now let's say if your x and y were real valued, okay, some Rn, then what is x dot y? Then your x dot y is nothing but summation I is equal to 1 to n ai bi, right? You take the, what do you do? Like when you take dot product of let's say 1 comma 2 dot 3 comma 4, you multiply the first element with the first one. That's what is happening over here, ai into bi plus second component with the second one, and so on. So when you extend it to any arbitrary like this field, then the second component has a conjugate on top of it. So if it would have been a complex plane, then this would have been a conjugate. This is how the first inner product is defined. So let's say if this satisfies our property or not. So first property says that x plus y comma z should be equal to x comma z plus y comma z. Let's look at its LHS. Okay. So the LHS is, so first of all, let's define some notation for x, y, and z. So my x look like a1, a2 till an, y looks like b1, b2 till bn, and my z looks like c1, c2 till cn. Okay. Then my left hand side can be, so if you take x plus y, it's nothing but a1 plus b1 and a2 plus b2 and so on. So now if you take x comma x plus y comma z, this is given by summation I is equal to 1 to n ai plus bi into ci conjugate, right? So because this is just this complex number is a field, so it will satisfy distributive property. So this is ai ci bar plus bi ci bar. So as this is summation, we can split it into 2 parts, and we obtain I is equal to 1 to n ai ci bar plus I is equal to 1 to n bi ci conjugate. So this is nothing but x comma z plus y comma z. So we satisfied our first property. Okay. Similarly, if you can see, proving the second property is also quite simple. That is, if you have cx comma let's say y, then what it is, this is I is equal to 1 to n c ai bi conjugate. So you can take the c outside, so this is just I is equal to 1 to n ai bi conjugate. So this is c times x comma y. This was also simple for us. Now the third property said that x comma y is nothing but y comma x conjugate. Okay, let's start with the right hand side this time. Okay, so what does this mean? This is given by I is equal to 1 to n, right? And this is your given by its whole conjugate, right? And then it is bi ai transpose. Now if you have, let's say, complex number c1 and c2, you take conjugate of both of them, then this is definitely equal to c1 conjugate plus c2 conjugate. Okay, so this becomes summation I is equal to 1 to n bi ai conjugate of the whole thing. Now if you break this thing, this would become bi conjugate ai conjugate conjugate, right? So now if you look at this carefully, right, so if you look at something like x plus iota y, if you take its conjugate, then it is x minus iota y. If you take one more conjugate, then this would be same as the initial one, right? So this is nothing but I is equal to 1 to n bi conjugate ai. As this thing is commutative, you can write I is equal to 1 to n ai bi conjugate, which is nothing but x y. Okay. Now in order to prove the fourth one, that is x comma x is greater than 0 for x not equal to 0, what we need to show is, let's say again my x is a1 a2 till an, then x comma x is given by summation I is equal to 1 to n ai conjugate. So if you take, let's say, x plus iota y and x minus iota y, what do you obtain? The x square plus y square, right? This is what you will obtain. So this is nothing but summation I is equal to 1 to n x square. So this is the mod of this x, that is the distance from origin for this complex number, because this thing is always positive. Okay, so this would be ai, this is ai square. So this thing will always be greater than equal to 0 unless all of your ai's is 0, which means your x would be 0. So if anything in this is non-zero, then you'll get this value to be non-zero. So whenever if you want to prove any function to be inner product, or you want to check whether it is an inner product or not, then you must satisfy all these four properties that we just checked. Okay, so whatever we defined over here, that was ai bi transpose, is indeed a inner product, and it is called as standard inner product. Okay. Just to remind, if there is any doubt, you can type it anytime, or you can just unmute yourself and stop me then and there. Okay. 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 Now we will move ourselves from normal vectors to matrices. Okay. So now we are given with a vector space of all n cross n matrices. Okay, and we have defined. So now you can see that the beauty of this generalization. When we had dot product, we were able to find angle between only two vectors. Now because we have generalized this to any arbitrary vector space, we can find angles between, let's say, two matrices, which is not visually very appealing, or we can not intuitively calculate that thing. Okay, so how we have defined this thing? This has been defined as trace of b star a. Okay, now this b star a is not b multiplied by a, but b star has a special meaning known as conjugate transpose. Okay, so what is conjugate transpose? So what you do is you just take the transpose of B and then calculate conjugate of every element. Okay, I'll take an example probably from the book only, so that, yeah, I'll take example from just a second. Okay, so let's say your A is such as given over here. Then what A star would mean is that first of all you need to take transpose, that is it would become I, and this would become 1 plus 2I. Okay, this would become 2, this would become 3 plus 4I, and then you need to take conjugate of every element. So it would become minus I, this would become 2, this will become 1 minus 2I, and this would become 3 minus 4 iota. Okay, so this is something that is defined as conjugate transpose. So how we have defined a trace? We have defined a trace to be, sorry, the inner product to be the trace of matrix B conjugate transpose multiplied by A. Okay, and we want to check whether whatever we have defined, whether it's an inner product or not. Okay, and just to mention that this this is indeed an inner product. We'll prove this in a while, but this inner product is something that is called as Frobenius inner product for matrices. Okay, and later you will see that if we like derive some norm out of it, that norm is called as the Frobenius norm. Okay, okay. Let's begin with the first property. What does the first property say? Let's say we have matrix A and some C, and we take its inner product with B, then it should be equal to A inner product with B plus C inner product with B. This is the first desired property that we want to show. Okay, let's break this thing. This would be trace of A plus, sorry, this is trace of B conjugate A plus C. Okay, so what is trace? Let's say this matrix is product P, then trace is nothing but PII, right? So what we can do is we can just keep writing like this only. So this is equal to trace of, we are just breaking the this matrix product. So this would be B transpose B conjugate A plus B conjugate C. Okay. Now if you have, let's say, two matrices, two matrices, okay, and you take the sum, and then you take the sum of diagonals, then isn't it same as if you take the sum of diagonals individually and then you add this thing? This is quite obvious, right? If so, even in the sum, the first element would be this plus this, so you can just take this individually from here and individually from here and then add them. Okay, so this thing is satisfied, so this is nothing but equal to AB plus CB. So we have satisfied the first property. Now second one is nothing but some C times A comma B is C times of AB. This is quite simple, so you can take this to be trace of B transpose CA. Okay, so if some matrix is multiplied by some constant, you can take that thing to be out of the trace, and this would be nothing but trace of B A. Okay, this one was quite simple. Now third one is that A B is equal to B A conjugate. Okay, let's start from this. So this is trace of A transpose B. Okay, so we just want to write this thing in terms of matrix multiplication. Okay, so let's say my matrix A was Aij. Okay, so then A conjugate will have form Aj conjugate. So my ith element became jth element and jth element become ith element. So when I transpose it, okay. So this is how it would look like. Okay. So if we want to find the trace, so what we want to do is I want to find the sum of the diagonals of this matrix multiplication. Okay. First of all, let's see how this matrix multiplication would look like. So let's say my I is from 1 to n and j is also from 1 to n. So what would happen is now my first row is getting multiplied by the first column. Okay. So for A transpose, this thing should be, that is my first row. Wait, it should be let's remove this thing. So if you want to find the product, let's say this matrix is something as P, then it's ith and jth element. So it is first row, okay, multiplied by into first column of B, that is ji. Is that right? And now we can do one thing, that is, if we want to write it in terms of A, then this would be nothing but j is equal to 1 to n. Okay, and this is Aji conjugate into Bji. We try to write it in form of elements of matrix A. Okay, now we just want the sum of the diagonals. Okay, so we want P of I comma form, right? So what we will do is we can take sum of elements where j is equal to I. Okay, so we can write the trace formula like this. So we'll have one more summation where I is from 1 to n, j is again from 1 to n, but we'll have summation as ai conjugate. Yes. No, I don't think so. So we just want the sum where j is equal to I. Just a second. J is equal to I. I think I have made a mistake over here. I should take something as k, right? K is equal to 1, and then I should run it all over k, and I take this thing as again k and this thing as j, right? Now I think it's better. Sorry for this. Okay, so this would be ik, this would be k j, and this summation should be k. This is how we do the matrix multiplication, right? We take the ith row and the kth column, and we take the dot product of both of them, right? So now if we take k over here, this is ik and multiplied by b of ki, because now we have I is equal to j. So this is the formula for our trace. Okay. So what we want is that this thing should be equal to this particular thing. So now we want trace of A transpose B conjugate. We want conjugate of this whole thing. Okay. So now moving from here to here, this is nothing but we can take this conjugate inside. Okay. And this would become aik conjugate conjugate into bki conjugate, which is nothing but I is equal to 1 to n, k is equal to 1 to n, aik into bki conjugate. Now again this thing is commutative as in previous case, so we can take this to be bki conjugate into aik, right? Now this is nothing but trace of B transpose A. If you just compare this and this thing, you can see that this is nothing but trace of B transpose A, right? So this is equal to A of B. Okay. So we have proved our third point also, right? Now only thing left to prove is that if A comma A, this should be greater than equal to 0. Okay. So this is trace of A transpose A. This is nothing but what we derived before, that this is AI K conjugate yeah, AI conjugate into this is A KI conjugate AKI. So this is again a complex number multiplied by its conjugate, then this would be equal to AKI norm for the modulus value of a complex number, right? So again, if not all terms of AKI are 0, then this summation of positive numbers should be greater than 0. Okay. So this way we prove all the 4 properties, and we can infer that this particular thing that we have defined, that is trace of P conjugate A, is indeed a inner product space, and this is called as the Frobenius inner product. Okay. Any doubt till now? Okay. Now we will try to prove some properties that comes sort of naturally from definition of inner product space. This I won't prove it very formally. I'll try to give an informal way how to prove this thing. Okay. Okay. Now if you look at this first one, it says that it should split even in the second component. It is claiming that it should be equal to x comma y plus x comma z. Okay. Now what we know is that this is equal to y plus z comma x conjugate, okay, using the third property of inner product space that we had. Okay, now because this is in the first place, then it can split. So this is x plus, sorry, this thing is y comma x plus z comma x, and we'll have a conjugate all over it. Now, as you know, this complex conjugate splits over addition, so we can write it as y comma x conjugate plus z comma x conjugate. What does this mean? This means that this is x comma y plus x comma z. This is what we needed to prove, right? So yes, even if you have summation in the second place, this thing will split. Now again, this property is very similar to one that we proved, that if we have x comma cy, then this is equal to c conjugate of x comma y. So when we had c at the first position, the c came out as it is. But if we have a scalar at the second position, then it will come out as its complex conjugate. Okay. So now this thing is also very easy to prove. You can write this as this is cy comma x conjugate. This is c into y comma x conjugate. This is again c conjugate into y comma x conjugate. This is c conjugate into x comma y. Right. So we are done with these two. Okay. Now again, if you have some, this I'll prove here only. If you have 0 over here, you can take, you can write this as x comma 0 into 0. This would give you 0 conjugate x comma 0, which is equal to 0 into x comma 0 is equal to 0. Similarly, for this one also, you can show that it is 0. So if you have 0 at any of the component, then its inner product with any vector would be 0. This is true, like, right? Even for the dot product, if you have 0 and you take dot product of 0 with any vector, then it is 0. Okay. This property we have already proved that this is equal to 0, greater than 0 if x is not equal to 0. This is from definition of inner product space. And it is 0 because if any of your component is 0, then it will be definitely 0. Now, E part is something that I'll prove bit formally. Okay, this says that if x comma y is equal to x inner product with z for all x, thing that you should keep in mind is that this thing is for all x. Then we need to show that y is equal to z. Okay. Okay. Let's proceed this way. We know that xy is equal to xz. If we take this thing on the left hand side, what we get? X comma y minus x comma z. This thing is 0. Okay. Now we can take this, because the first component is matching, we can write it as y minus z. This is equal to 0. Right. Now, if we take, because it is true for all x, if we take x is equal to y minus z, then what does this give? This gives that y minus z inner product with itself is also 0. Okay. Now using the previous property that it is 0 if and only if x is 0. What does this mean? This means y minus z is 0 or y is equal to z. Okay. I would like to mention two more inner product spaces, which I'm not going to prove whether it's inner product or not, because it would take a lot of time. We can do other interesting things with our time. So these two inner product spaces are defined over the space of functions. So if you have fx and gx to be two functions, okay, so its domain must be between 0 to 1, right? Then you can define the inner product as integration of ft into gt from 0 to 1. Okay. This you can show, or you can use, like whenever you have to use, as a valid inner product. Similarly, you can take, if you take integration from -1 to 1, you get another inner product on functions. Okay, these are two inner product spaces that I just wanted to mention, and you can use it in your applications. Okay, any doubt with the definition of inner product or properties of inner product, so that I can move ahead? Okay then. Okay. Now, if you talk about angles, right? When we talked about angles between two vectors in our school time, one thing that we talked about was something called as the perpendicular vector. Okay. So, what is the property of a perpendicular vector in terms of dot product? So, if you have, let's say, vector v1, which is perpendicular to v2, what is v1 dot product with v2? That would always be 0. Okay. So, v1 dot v2 is v1 v2 cos theta, and cos 90 is 0. Right. So, if you have two perpendicular vectors, then their dot product is 0. So, a generalization for this perpendicular vector is something called as orthogonal vectors. Okay. So, two vectors v1 and v2 are called orthogonal if dot product between v1 and v2 is 0. So, this is just a simple example. I'll give you an example. Let's say we have our vector space as R2 over R. Okay. Then we can define v1 to be 1 comma minus 1 and v2 to be 1 comma 1, and like v1 comma v2 as the standard inner product. What was standard inner product? So this is nothing but summation of ai bi conjugate I is equal to 1 to n, but because everything is from real number, so this is nothing but your dot product. Okay. So you can verify that v1 dot v2 is nothing but 1 into 1 plus minus 1 into 1, which is equal to 0. So these two are orthogonal vectors. Can you give me one more set of orthogonal vectors for R2? I want you to give me two vectors in R2 which are orthogonal to each other. Satyajit, I'm muting you. Yeah, you muted those two things. I want two vectors in R2 which are different from this set of vectors that I've already written, which are orthogonal to each other, or their dot product would be 0. You can type in chat box, or this is or you can unmute yourself also. Any two vectors that you can recall which you think their dot product would be 0. One simple one is if you take 1 0 and you take 0 1, that is your standard basis. So this would be 1 into 0 as 0 plus 0. Again their dot product would be 0, right? So this is another set of orthogonal vectors. Okay. So you can construct many orthogonal vectors. Okay. Okay. Again, any doubt in inner product space, now we'll move to something called norms, and then we'll try to link both of these things. So if inner product space is not clear to you, then norm won't be clear to you either. Okay, Now, when we talk about geometry of any object, or let's say some lines, okay, so we generally talk about two things. Okay, let's say you have two lines, something like this. Okay, so one thing is that you talk about angle between these two vectors, right? Another thing that you talk about is the length of the line. Okay, now we had a notion of angle between two lines. We defined the notion of angle between lines. Now we want to generalize the notion of length of a line, okay, or length of a vector. If you recall, let's say you have a point like 1, 2, that is, okay, yeah. So let's say you have a point over here, okay, which is 1, 2. Then how do you define length of this vector? You used to do 2 minus 0 square plus, okay, no, not 2 minus 0 square. You just used to do 2 square, okay, plus 1 square. What it is? This is square root of 5, okay. This is how you obtain length of a line in your schools. Now if you break this thing, you can view this as 2 into 2 plus 1 into 1, right? Again, if you break this thing, you can view this as 2 comma 1 dot 2 comma 1. So this is dot product of the vector with itself, okay. So that's how it became 2 into 2 plus 1 into 1. So from this idea, we can generalize the notion of distance. As we discussed that we can have more than one inner product on some space. So now from that particular inner product, we can define length of vector x, okay, as the square root of norm of x with itself, okay. And this notion of length is something that is called as norm of a vector, okay. So how do we define a norm? We just take inner product between vector and itself, and then we take a square root of it, very similar to what we were doing in our schools, okay. So let's say we have Fn where the dot product is your standard inner product, okay. Then what we would have got, x comma x was summation I is equal to 1 to n xi conjugate. This is I is equal to 1 to n xi square, right? And we want to take square root of this thing in order to obtain a norm. We want to take square root of this thing. So this is what is written over here, that we take square of every element when we take power 1 by 2. Okay. Now I'd like to mention few more norms on Fn. Okay. So this is something that is called as the 2 norm or the Euclidean norm. If you read, many people will say this as a Euclidean norm. So whatever geometry we studied in our schools that was related to length or angles, that geometry is called something as the Euclidean geometry. Okay. We have more forms of geometry, like if you go for higher education mathematics, then you'll encounter more forms of geometry. Okay. Now talking about norms, this is called 2 norm. Okay. Why it is called 2 norm? Because we have 2 over here at both these places. Okay. We have 2 over here at both these places. If we now replace this 2 by some p, okay, then that norm is something as called as p norm. Okay, so if you have something like this, I is equal to 1 to n mod of a is length of a. So if it is a complex number, then it would be length of it, or if it is a real number, then it would be just the modulus or mod of a. So if I take any p over here, then this value will be always positive. Okay, then I take 1 by p. This is something called as p norm. Okay, how would a 1 norm look now? So a 1 norm would look like summation I is equal to 1 to n mod ai. Power 1 and power 1 by 1 doesn't make any sense. So if you have something like 1 comma 2 comma 3, then its 1 norm is given by mod of 1 plus mod of 2 plus mod of 3, which is nothing but 6. Okay, so you have different notion of length now. Okay, this is something called as 1 norm. Okay, okay. Now we derived something called as norm from inner product space. Okay, I think these properties were discussed by Professor Rana also, but the proof was missing for C and D part. I'll try to include proof over here. Okay, now what we want to do is we want to prove that these 4 statements are true. First 2 statements are quite trivial, but the last 2 are used very widely. Okay, so this is called as Cauchy-Schwarz inequality and triangle inequality. Okay, okay. First one is that C of x is equal to mod of C times x. Okay, now remember that how did we obtain norm of x? The only thing that we know about norm of x is this thing right now. Just give me a minute. Okay, so let's replace this definition of norm of x on the left hand side. Then we obtained cx comma cx. Okay, now this c can come out. For the next c, what would come out is C transpose from the property of inner product space. Inner product, not space, sorry. Yeah. And we will be left with this. Now this C into C transpose is mod C square, and this is norm of x square. What we obtain? Mod C into norm of x. So this first one is quite easy and quite straightforward. So we have done that. Second one is norm is 0 if and only if x is 0. Okay, and in any case x is greater than or equal to 0. If you remember what we proved, that this thing is always equal to 0 if x is not equal to 0. What would it mean? This would mean that norm of x square, okay, is always greater than 0, or its square root is always greater than 0. So this square over here is not with respect, like you are not solving any polynomial for roots over here. Okay, because if you have let's say square root of 4, then you take that value to be 2, right? But when you try to solve something like x square is equal to 4, then you say x is equal to 2 comma minus 2, both satisfies your value. Okay, square root of 4 is also equal to minus 2, but in case of norms we only stick to positive values. Okay, so these two properties were quite simple. I'll straight away move to Cauchy-Schwarz inequality. Okay, now what does Cauchy-Schwarz inequality say? This says that if you take inner product between x and y and you take mod of it, this thing is strictly less, okay, then if you take mod of x into norm of y. Okay, this is not dot product over here because these are scalar values. This is just multiplication. Okay, we want to prove this thing, that norm of x comma y is strictly less than norm of x into norm of y. Okay, one way to do is that we know that if x minus cy is anything, then its norm square would always be greater than equal to 0. Okay, we will use this thing. This is very like simple but not very intuitive, but we'll use this thing to reach our result. Okay, so now if you look at this right hand side, what is this equal to? This is equal to x minus cy comma x minus cy, inner product between this thing. This is how we define the norm. Okay, now if we break the first one, this is x comma x minus cy minus c times y x minus cy. We can do this using the property of inner product space. Now we'll try to break the second one also. Okay, then this thing is equal to x comma x minus c conjugate, because c is coming out from the right side of the inner product. Okay, x comma y, this one you will get, this is y. Okay, minus c times y comma x. Okay, and then you will get something as minus of minus, that is plus c into c conjugate y comma y. So c from here and c conjugate coming out from here, and this minus and minus becomes plus. Okay, now what we have obtained is this, whatever quantity we have written over here, okay, this thing is strictly greater than equal to 0. This is what we have obtained till now. Okay, now if we take our c to be inner product of x comma y, okay, divided by y comma y, okay, we want to see what we get. Okay, like if you intuitively look at it, what it is, so, okay, I'll come to the intuition later on. Okay, we just now need to replace this thing over here. Okay, what we would get is x minus x, sorry, this is inner product between x comma x minus c transpose or conjugate. This is c. If we replace now, what we get is x comma y conjugate divided by y comma y conjugate into x comma y. Okay, this is minus x comma y into y comma x. Okay, divided by y comma y, and this is plus x comma y into x comma y conjugate divided by y comma y into y comma y and again a y comma y, right? And this thing we know is greater than equal to 0. Okay, let's see what we can make out of it. We'll try to do something with it. So this first term I can write as norm of x square. Okay, now if you look at this thing, x comma y conjugate is nothing but y comma x, right? So now if you look carefully, the term in the denominator is y comma y conjugate. Even if you take the conjugate and we reverse the role, then it will be again y comma y only. So let's replace this y comma y by norm of y square. Okay, and we have a similar term over here, so we can take this to be 2 times. Okay, and in the last we have this y and this one gets cancelled, so this is again this is same term y comma x into x comma y divided by norm of y square, and this thing is greater than 0. If we take sum of these two terms, what it is, this is minus of y comma x into x comma y. Wait, yeah, y square. Okay, now what does this mean? This means that x square into norm of y square minus, if you look at this term carefully, this is nothing but x comma y conjugate into x comma y. What it would be? This would be length of this x comma y. Okay, so this is x comma y is greater than equal to 0. So what I did is I took this y square this side and then multiplied it by 0. Okay, so this would mean that my norm of x square, this would be square of the length, sorry, yeah, into y square is greater than equal to, now if squares are greater than, so we can take the square root both side, and this is what we had to prove. Okay, so this is something that is called as Cauchy-Schwarz inequality.
Hello, sir.
Hello.
Repeat again.
What do you want me to repeat?
सर ये पूरा फिर से रिपीट कर.
ठीक है, देखो इसके प्रूफ में ना 2 ट्रिक हैं खाली. Okay, there are 2 tricks in this proof. Not tricks, but things that you should remember. Okay, what you need to do is you need to see that 0 is always less than equal to x minus cy norm square, right? If you have norm of anything, that would be always greater than equal to 0. Okay, the thing to remember is what should you write inside. Okay, ये ठीक है अगर इतना किया, this is okay. So now what we will do is we will write this norm in terms of inner product space. ठीक है, ऐसे लिख देंगे, and then we will expand it. ठीक है, जहां तक possible है उसको expand कर देंगे. So what I did is I'll expand it again for you, but I'm just giving you the outline of the proof first, so that when I do it again, it will be clear to you. ठीक है, then we will expand it. जहां तक expand हो सकता है, we'll expand it completely. ठीक है। नाउ बिकॉज दिस थिंग वॉज ग्रेटर देन इक्वल टू 0, जो भी एक्सपेंड करके आएगा वो भी ग्रेटर देन इक्वल टू 0 रहेगा। ठीक है। नाउ इन द नेक्स्ट स्टेप व्हाट वी विल डू इज we will take c to be something as this, ठीक है, x minus y divided by x inner product with y divided by y inner product with y। ठीक है, हम c को इस वैल्यू से रिप्लेस कर देंगे। जब हम रिप्लेस कर देंगे तो सॉल्व करने के बाद हमें ये इनइक्वालिटी मिल जाएगी। ठीक है, अब आउटलाइन क्लियर है?
सर उसका
हाँ बोलो बोलो बोलो।
एक्सपेंड फॉर्म फिर
हाँ वो पूरा मैं करके दिखा रहा हूँ दोबारा से, पर आइडिया ये है। ठीक है, इफ द आइडिया इज क्लियर देन इट विल बी मोर क्लियर टू यू व्हेन आई एक्सप्लेन। ठीक है, तो अब इसको एक्सपेंड करने के लिए हम लोग क्या करेंगे, फर्स्ट वाले को पहले ब्रेक करते हैं। तो दिस वुड बी x माइनस सी वाई। ठीक है, माइनस बाहर आ गया c ट्रांसपोज के साथ। चलो मैं एक एक स्टेप वाइज ही करता हूँ। ठीक है, प्लस क्या रहेगा ये माइनस सी वाई कॉमा एक्स माइनस सी वाई।
एक्स माइनस सी वाई।
ठीक है, अब इस वाले को फिर से हम लोग दो पार्ट में ब्रेक कर रहे हैं, x कॉमा एक्स प्लस
एंड
x कॉमा माइनस
माइनस
सी
सी
वाई।
वाई।
ठीक है, प्लस माइनस सी वाई कॉमा एक्स प्लस माइनस सी वाई कॉमा माइनस सी वाई। ठीक है, अब x कॉमा एक्स क्या बन जाएगा हम लोग का, नॉर्म ऑफ एक्स
मॉड
स्क्वायर।
एक्स स्क्वायर वो किया।
इसमें से c बाहर आया तो व्हाट वुड इट बिकम, दिस वुड बी माइनस माइनस ऑफ c टाइम्स x comma y, this would become minus c of y comma x। ठीक है, और दिस वन यहाँ पे एक कॉन्जुगेट भी आएगा बिकॉज वी आर टेकिंग c फ्रॉम द राइट वन, राइट। और यहाँ पे क्या आएगा, c कॉन्जुगेट माइनस माइनस हो जाएगा प्लस y comma y। ठीक है, और इस ये किसके इक्वल है, y comma y, y comma y तुम्हारा इक्वल
मॉड
होता
वाई
है
स्क्वायर।
मॉड y स्क्वायर। ठीक है, अब एक स्टेप हो गया, वी हैव एक्सपेंडेड दिस थिंग। ठीक है, अब हम लोग दूसरा स्टेप करेंगे, c को लेंगे x कॉमा वाई डिवाइड बाय नॉर्म y का स्क्वायर। ठीक है, इसको हर जगह रिप्लेस कर देंगे।
सर तो ये हमने ये
बोलो।
यहाँ से सेकेंड लाइन से सी को आपने कॉमन लिया तो इसमें एक्स में तो सी नहीं है, फिर हम लोग कहाँ से ले सकते हैं सी कॉमन?
कहाँ पे, लास्ट वाले टर्म में x में c नहीं है,
लास्ट से
यहाँ पे
फर्स्ट।
c नहीं रहेंगे, यहाँ पे c नहीं रहेगा, यहाँ पे ऐसा ही रहेगा।
नहीं, इसके बाद वाले
अच्छा यहाँ पे क्या, देखो
तीन
इस इक्वेशन में, अच्छा इक्वेशन में
एक्स
हम
कॉमा माइनस सी वाई में से सी।
यहाँ पे, हेलो, इसमें y में c था ना, तो जो हमारा इनर प्रोडक्ट का प्रॉपर्टी होता है, इफ यू हैव लेट्स से सी एक्स कॉमा वाई किसी एक में भी है, अगर पहले वाले के साथ में है तो वो एज इट इज बाहर आ जाता है। ठीक है, अगर वो दूसरे वाले के साथ है, मान लो एक्स कॉमा सी वाई है, तो वो सी कॉन्जुगेट बन के बाहर आ जाता है। दिस इज प्रॉपर्टी ऑफ योर इनर प्रोडक्ट स्पेस। ठीक है, जरूरी नहीं है कि दोनों में रहे, अगर दोनों में रहेगा तो पहले वाले में से सी बाहर आएगा और दूसरे टाइम में से सी ट्रांसपोज बाहर, ये
और
सी
दूसरे वाले
कॉन्जुगेट
में से सी।
कॉन्जुगेट बाहर, जैसे यहाँ पे हुआ, यहाँ से सी आया, यहाँ से सी कॉन्जुगेट आया। ठीक है, अब हम लोग क्या करेंगे, विल रिप्लेस सी बाय दिस थिंग। तो पहला टर्म तो एज इट, और ये चीज क्या है हमारा, ग्रेटर देन इक्वल टू 0 है, तो पहला टर्म तो एज इट इज रह गया हमारा। दूसरे वाले में सी है, तो सी क्या बन जाएगा हमारा, सी वुड बिकम माइनस एक्स वाई कॉन्जुगेट divided by y square into xy.
So how many sessions still remaining?
So this is 6th week. So this course is 8 weeks, so there will be 2 more tutorials for this course.
Okay, thank you.
Okay. So, and तो उसके आगे होगा c would be x comma y divided by into y comma x. Now you can again write y comma x as x comma y conjugate, है ना, by property of your inner product space. और लास्ट
Yeah.
में क्या है, x comma y, चलो ऐसे लिखते हैं, बाय ये स्क्वायर and this is your x comma y conjugate divided by y square, right, or into y square. This is greater than equal to 0. एक कैंसिल हो गया, ठीक है. अब हम लोग कुछ नहीं कर रहे हैं, हम लोग को विल टेक दिस y स्क्वायर टू बी कॉमन. इफ यू सी दिस इज x स्क्वायर, चलो एक एक स्टेप ही करते
Yeah.
हैं फ्रेंड. दिस इज -2 प्लस सेम थिंग एक बार ऐड हो रहा है, तो दिस वुड बी xy conjugate into xy divided by, this is greater than equal to 0. अब जो thing, this thing on the top, this is nothing but mod of xy square. कोई if you have a complex number c, then what is c into c conjugate? This is mod of c square, right? This is
Mod
greater than
C
equal to
square.
0. अब इसको इधर ले जाएंगे and we'll get whatever we want. ठीक है. Now we'll move to something called as triangle inequality. So we had 4 property for our norms, right? First 2 were quite easy. Third one was the Cauchy-Schwarz inequality. Fourth one is something that is called as triangle inequality. Okay. What does this say? That x plus y is less than mod of x plus. To prove this thing, what we'll try to prove is, we'll try to prove that x plus y norm square is less than x plus, this is x plus norm y whole square. If we prove this thing also, then also we'll be proving this only, right? These two are very equivalent statements. If you have a less than b, then a square is also less than b, or vice versa.
Yeah.
Okay. So let's start from here. Okay. So we have x plus y norm square. Why are we taking norm? Because we don't want to work with square roots, right? This way, this would be very easy. Again, we will have to split this thing. So this would be xx plus xy, right? xx plus xy plus yx, right? And plus y. This is quite very simple. We'll first split the first one and then the second one. So this is norm of x square plus xy plus xy conjugate plus
Mod Y square.
yeah. Now if we have a complex number c and we take its sum with conjugate, what would we get is, we would get 2 times of real part of c. Okay. So if you have x plus iota y, and if you add its conjugate,
X minus iota Y.
so this would be 2 times of its real part. Okay. So this can be written as 2 times of real part of x comma y. Okay. Plus norm of y. So I have taken a mod over here, that is, I'm taking the positive value of whatever my real part is. That's why I have included a less than equal to sign. ठीक है, तो ये जो है x plus y का real part, x comma y का real part, either it could be positive or it could be negative. So I am taking only the positive possibility. तो अगर यहाँ पे नेगेटिव वाला भी लेते हैं इसमें, तो that will be always less than if we take replace this thing by positive. That's why we have taken a less than equal to sign rather than equal to now. Okay. अब if we just look at the mod of the real part, okay. So let's say you have a complex number 3 plus some iota y, then what is the length of let's say this is z, then what is norm of z? This is 3 square
3
plus
square plus y square का root.
right. So if you look at this thing will be always greater than if you take mod of just the real part. अगर हम बस रियल पार्ट का मॉड ले लें और पूरे का लेंथ निकाल लें, then पूरे का length will always be greater than real part, because in this we are adding this y square term. No matter how small this is, but this will be always greater than equal to. Okay. So now what we are saying that x square plus 2 times of x comma y plus y square. So this is length पूरे का, ठीक है, और this was length of just the real part, ठीक है. So this is always less than equal to this thing. Now we use our Cauchy-Schwarz inequality over here. Cauchy-Schwarz inequality क्या बोलता है? That this thing is always less than equal to norm of x into norm of y. That we proved just now. Less than equal to. और ये किसके equal है? This is equal to norm of x plus norm of y whole square. And this is what we wanted to show, that this quantity x plus y square is less than equal to norm of x plus norm of y whole square. Okay. So this is something that is referred as triangle inequality, and metric spaces also inherit this thing from this norm space. Okay. Okay. Okay, now we need to talk something about orthonormal vectors. We talked about orthogonal vectors. What were orthogonal vectors? V1 and V2 were orthogonal. If V1, V2 was 0. Now we call V1 and V2 as orthonormal if first property is that V1 and V2 are orthogonal, that they need to be orthogonal. And the second thing is that norm of V1 should be equal to norm of V2, that is equal to 1. That is, all of them should be length 1 vectors. Okay. So you can extend this definition to any arbitrary n, that is V1 plus V2, V1, V2, Vn are orthogonal or orthonormal if Vi comma Vk is equal to 0, that is they are orthogonal with respect to each other, and all these Vi's, norm of Vi's should be 1. Okay. Okay. So till now what we have done is we defined inner product and use that inner product to define a norm from inner product. But one thing I want to mention, probably this was not covered in the course, but I thought it is useful. So one thing that I want to mention is that it is not necessary that your norm comes only from inner product. Okay, what I mean is that it is not necessary that any kind of length that you define on a space, that should always come from some inner product. That is not necessary. Okay. So norm itself also has a independent definition in itself. Okay. What is its definition? So if you look at this definition carefully, these are the properties that we just proved. Okay, apart from Cauchy-Schwarz inequality, these are the properties that we just proved. Okay, so if you have a vector x from some vector space V and F is your field, then any function x, something like this, is called a norm if it satisfies these three properties. First one is that it should be always greater than or equal to 0. You think very intuitively. So if you have length of anything, the length should always be greater than or equal to 0. And it is 0 only if your vector is 0 itself. This is the first property of a norm. Okay. Second property is, if you scale this vector by some factor a, let's say you had a line, you doubled the line. Okay. So its length should be mod of a times x. Okay. So now one thing is that you have mod of a, because you don't take care of the like the direction in which you are going when you are talking about length of a vector, right? Let's say you have a vector in this direction, but you now reverse. So let's say you have a vector in this direction, but now you reverse the direction of the vector, and you twice like took two vectors in the same direction. Then its length would be 2 times of length of this vector only, right? So this is the second property. And third one is something that is called as triangle inequality. So one thing just to mention is that it is not necessary that you need an inner product space to define a norm. You can define a norm independently also. Okay. So all the norms that we talked about, that is a 2 norm or P norm, would satisfy all these three properties also. Okay. Okay. Now there is a important question, that one thing we know is that if we have an inner product space or an inner product, I won't say space over here, then that leads to a norm. Okay. And now I also gave you a definition of like a norm. If you don't have an inner product space, you can directly define a norm. Now the question is, does every norm have a associated inner product? So the question is, if you define a norm using these three properties, like you just defined a norm using these three properties, is it necessary that you have an inner product in the back end so that that inner product will lead to this norm? Okay. So the answer actually is no. You can have many norms so that it is not induced by inner product, and we'll try to have a look at some of them. I'll give you one or two examples. Okay. Now, to prove or sort of see that thing, we need something that is called as parallelogram law. Okay. So if you have a norm induced from an inner product space, inner products or an inner product, I'm not sure why I'm saying space again and again. So if you have a norm that is induced from an inner product, then that norm should satisfy this property. Okay. So if this particular norm is something like this square root, then this should satisfy this property. We'll have a very small verification for this. Okay. So on the left we have x plus y comma x plus y. Because it is induced from some norm, we can write it in this form, x minus y comma x minus y. Okay. If we expand this thing, this is nothing but x comma x plus x comma y plus y comma x plus y comma y. For the second one, this is x comma x plus minus of y comma x, okay, minus of x comma y and then y comma y. So this thing gets cancelled by this thing gets cancelled by this, and what we are left with is norm of 2 times norm of x square plus 2 times norm of y square. This is very simple, right? You just need to expand the thing on the left hand side. Okay. Okay. So what I meant is, like, if you have any norm that is derived from this inner product space, then that should satisfy this kind of property. So if you have some norm that is not satisfying this property, then that would mean that it is not derived from some inner product space. Okay. Okay. So we will present example that is not derived from a norm. Okay. So let's say you have x is equal to some x1, x2, xn. These are all, let's say, let it belong to Rn only. That is your n-dimensional vector. When I was defining norm, I mentioned that we can define one norm like mod of x1 plus mod of x2, so on till mod of xn. Okay. Now, if you look at this thing, let's say my x is 1 comma 1 and y is my 1 comma minus 1. Let's see if this satisfies parallelogram law. Okay. So what we want to do is, we want to do x plus y square plus x minus y square. Okay. So x plus y would be 1 plus 1 is 2 comma 0 norm square plus this is 0 comma 2 norm square. Okay. So what is the norm that we have? Norm is the 1 norm. So what is norm for 2 comma 0? 1 norm is mod of 2 plus mod of 0, that is 2. Okay. Similarly for this one. So what is this equal to? 4 plus 4 is equal to 8. Now let's look at the right hand side. That is 2 times norm of x square plus norm of y square. Okay. I think for this particular case, it would be satisfied. Okay. So, okay, now let's look at this. What is norm of x? This is norm of 1 plus norm of 1, that is 2. Okay. Again, this norm is also 1 plus 1, that is 2. Yeah. 2, then again it's right. So what is this sum? This is 2 into 2 square plus 2 square, right? Norm is 2, and 2 into 2 square. So this is 2 into 8, which is equal to 16. So for the norm that we define, this parallelogram is not satisfied. Okay. What does this mean? This means that this norm that we had is not induced from any of the inner product space. This is not induced from inner product. Okay. This is not induced from inner product. So what I mean to say is that you can have norms, okay? You can have norms which is not induced from inner product. An example that you know is 1 norm for Rn. Okay. In fact, if you look at P norms, then for P is equal to 2, it is induced from standard inner product, that is dot product. Okay, standard inner product. And for other P's, it is not induced from any norm. Okay, it is not induced from any inner product. So if you just would have checked for the same vector for P is equal to 2, this would have satisfied, that the parallelogram would have satisfied. And if you check it for any other P, then the parallelogram would not satisfy. Okay. Okay. Now one more thing that I mentioned in the heading was something called as a matrix norm. We talked, so this whatever we have over here is related to some vectors. Matrix can also be viewed as a vector, but if you talk about matrix, then it has some extra property that it satisfies. The property that it satisfies is that the product of AV, if you take product of A and B and you take its norm, then that is always less than norm of A into norm of B. So if you look at this definition of norm, then these three properties must be satisfied. That is, norm of A should be greater than equal to 0, and norm of A is equal to 0 if and only if A is equal to 0. And the second property was some C times norm of A should be equal to C times norm of A. Third one was that A plus B should be less than equal to norm of A plus norm of B. But apart from it, one more property that should be satisfied is that product of AB is always less than equal to norm of A into norm of B. Okay, I just wanted to mention it. Probably it won't be used right now, but it is used many places in numerical analysis, or if you go for functional analysis, at those places this kind of becomes useful. Okay. Okay, I had two norms that I wanted to prove using the definition of norm, but I'll come to it at the end because I have around 25 minutes left and I want to cover other things also. Okay, I'll come to it at the end because this is just using or proving these three definitions over here, putting in definition and proving. Okay. Now we talked about inner product. Okay. We talked about length of a vector. Okay. Another geometrical quantity that is interesting is distance between 2 points, right? Geometry is incomplete without distance between 2 points, right? So this is very briefly that I'll talk about this is, so if you want to find distance between 2 points, okay, you can define a generic distance formula between point x and y. Let's denote it by d. You are denoting inner product by this symbol, norm by this symbol, and distance will denote by d. Okay, so distance between x and y can be given by a function that satisfies these four properties. Okay, what are these four properties? That the distance of a point from itself must be 0. Very intuitive, right? So distance of a point from itself must be 0. Distance between any 2 points should be always greater than equal to 0. If my x and y are not equal, then the distance between any 2 points should be always greater than 0. Intuitive. Third one is something called as triangle inequality. Okay. And the fourth property is that my distance between x and y must be equal to distance between y and x. If I go from x to y or I come from y to x, then its distance should be same. So if any function satisfies these four properties, okay, then it is called as a metric or a distance, you can say. This d is called a metric. Okay. Now from inner product we reach till norm. Now what I am saying is, from every norm we can define a notion of distance. Okay, how can we define that thing is, like if we take distance between 2 points to be the norm of this vector, that is x minus y. If we take norm of this vector, then this defines a distance. You can verify that this will satisfy all these 3-4 properties whatever we have written over here. Okay, I won't go into details, but yeah, you can define from norm, you can get a distance. Okay. Okay. Now again the same question comes into picture, that for every like for a norm, was it necessary that it should come from some inner product? Okay, because we have a separate definition for norm. The same question arises over here also, that whether for every distance or a metric that we have, do we have a corresponding norm? Okay, so I'll define a matrix that is called as discrete matrix. How do we define a discrete matrix? D of xy is given as 0 if your x is equal to y and 1 otherwise. What we mean is, if your points are same, x and y are same, then you say that the distance between these 2 points is 0. But if your x is not equal to y, then you take the distance as 1. So distance between any 2 points is always 1. This is something that is called as discrete matrix. If you look at these properties, d of x is equal to 0 is satisfied, this one is satisfied. X comma y is always greater than 0, this is also satisfied. The last one is also satisfied. Triangle inequality also you can satisfy, right? D of x comma y is less than equal to d of x comma z plus d of y comma z. So this would be 1 and this would be always less than 1 or 1, that is 2. If x and y is same, then this is 0, then obviously it would be less than equal to this. If x and z is equal, then 0 plus 1. In any case, like if you take any combination, this thing would be satisfied. Okay. Okay. So if you look at this discrete matrix now, then if this, let's say, came from a norm, okay, there is a norm so that x minus y is 1 for all x not equal to y. Okay. Now there is a property of norm that ax must be equal to mod of a into mod of x. Now if you take x to be x by 2 and y to be y by 2, then what is this norm? This is half norm of x minus y, and by property of norm this should be half. But what we said is that in any case this norm or the distance should always be 1. So there is no norm which induces this discrete matrix. Okay. Okay, just to summarize whatever we talked in last 20-25 minutes, we have some notion of inner product. Inner product leads to something called as norm, and we have a norm which is not equal to which is not induced from inner product. An example is one norm on Rn, and then this norm leads to something called as metric, and we again have an example of metric which is not induced from a norm. Any doubt on this? Then we will move to a Gram-Schmidt's orthogonalization process. We'll ignore this thing right now, and if time permits, we'll come back to it. Any doubt on this? Okay. Okay. We have some 20 minutes, so I'll try to cover something that is called as Gram-Schmidt's process. So what is this process useful for? So if you have, let's say, some set of linearly independent vectors, this process is used to make these linearly independent vectors as orthogonal vectors. Okay. So if you have this orthogonal representation for basis, then you can look at something called as let's say singular value decomposition or those kind of things, where you need basis vectors to be orthogonal. Okay. Or like if you want to look at the projections of some vector on basis vectors, because these orthogonal vectors are these basis vectors are orthogonal, then the projection can sum to form the same vector again. So there are many geometric and other benefits of finding an orthogonal basis. Okay. So that probably I won't cover today, but I'll cover how do we convert any set of linearly independent vectors to orthogonal vectors. One thing that you should remember is that if you have a set of orthogonal vectors, then they are always linearly independent. Okay. So if you have orthogonal vectors, then they will be always linearly independent. So now we have to see the other way around. Like if you have linearly independent vectors, you want to convert it to orthogonal vectors. Okay. Before that, let's look at a very small thing, that is a projection. What we mean by projection. Okay. Okay. Let's say you have a vector A. Okay. You have a vector V. You want to find this length of this projection. Projection is like if you draw a 90-degree angle line that intersect this thing at 90-degree, then what is length of this vector? That this is what you want to find. Okay. So let's go by this dot product thing. So if this angle is theta, what is this? Let's say this is norm A, this length of this vector is norm A. Then this thing is given by A cos theta, right? So cos theta is base upon hypotenuse. Let's say this is my base, hypotenuse is norm A. I take this thing this side, I get base to be A cos theta. Okay. Okay. So we want to find this thing, right? That is norm of A cos theta. We want to find in terms of dot product. So let's say if you have A dot B, then you can find this A cos theta as A dot B divided by norm of B. Okay. So projection of A on B is given by
A dot B by mod B.
yeah. So like what intuitively we are looking at is, so let's say we have some other vectors also. Now if we subtract this thing from A, okay, then we won't have anything left that correspond to this like direction of our vector B. Okay. This is what we meant by projection. Now we had projection in terms of dot product. If we extend this again to our inner product, then it is given by A inner product B divided by norm of B. This is the projection. Okay. Okay. I'll go slow here. Now, next thing that we want to talk about is, let's say you had some basis. Let's say you have basis V1, V2, Vn. Okay. Then If you want to represent, let's say, a vector u in terms of a1 v1 plus a2 v2 plus an vn, then till now what you used to do is you had to solve a system of equation to find this values of a1, a2 and so on, right? This is what you had to do. Now what I'm saying is, if my let's say v1, v2, vn is orthogonal, okay, then we need not solve like a complex system of equation to get this value. I'll give you an example. Okay, let's look at 2D space. Okay, so let's say I have a vector something like this. Okay, now you see that for a two-dimensional R2, what you have is why is it not working? Wait. Give me a second. A window. Yeah. For R2, you have a orthogonal basis as 1, 0 and 0, 1. Okay. So what is 1, 0 is your x-axis. Okay. This is y-axis. Okay. Let's say this point is 2, 5. How do you write 2, 5 in terms of this? Okay, this is actually not 2, 5. Let's say this is 2, 3. Let's be pretty realistic. So how do we write 2, 3? We look at its x component. That is, we look at if we project it on x, what is its length? Its length would be 2. Now if you projected it on y-axis, its length would be 3. So how do we write 2, 3? We write 2 multiplied by 1, 0 plus 3 multiplied by 0, 1. So what we did is, we looked at the projection onto first orthogonal axis, and that came out to be the value of a1. Okay, and when we looked at its projection on the second one, that came out to be value of a2. What I am saying is, similar thing will happen if we have orthogonal basis for any arbitrary vector space. Let's say we have v1, v2, vn, okay, and these are orthogonal, that are they are perpendicular to each other in some sense. Okay, then if you want to write some vector v in terms of a1 v1 plus a2 v2 plus an vn, then we need not solve a system of equation to obtain this a1 and a2, but a1 can be given as projection of v onto v1, then a2 can be similarly given as projection of v onto v2, okay, and so on. So this is what is given by this theorem. Okay, what does this say? Let's say we have V is a inner product space. That means we have a inner product space defined on it. Okay, and S is an orthogonal subset of V. Okay, now if Y belongs to span of S, that just mean that we want to write Y as A1 V1, so on. Then your Y is given as summation of, this is projection, right? This is, so if you expand this, this would be something as y comma v1 dot v1 square norm square, right, into v1. Okay, so this is nothing but the projection of v1 in what direction? So I'll split it further. just give me a second. Yeah, this is y comma v1 by norm of v1 into v1 by norm of v1, right, plus y comma v2 by norm of v2 into v2 by norm of v2, and so on. So this is just the projection of this y on v1 in direction of v1. This is just v1 and we have normalized it, just normalized it so that we get a unit vector in that direction. Okay, plus again the same thing. So this is how you can obtain a1, a2, a3 directly. If you want to prove this thing, the proof is also very easy. Okay, so there is almost nothing in the proof. So let's say your y is a1 v1 plus a2 v2 and so on, a and vn. Okay, now you take inner product with respect to v1 on both the side. What we obtain is y comma v1 is equal to a1 v1 comma v1 plus a2 v2 comma v2 and so on. So because now this v1, v2 and v3 are orthogonal, so everything except of this first term would be 0. This everything would be 0 because v1 is orthogonal to all these vectors. So what this gives? This gives y comma v1 is equal to a1 times v1 comma v1. This implies a1 is equal to y comma v1 divided by v1 comma v1, which is y comma v1 divided by norm of v1 square. So similarly, you can find a3 and ai's respectively. Okay. Okay. Now we had this beautiful property. If my v1, v2, vn were orthogonal, right? What if my vy's are not orthogonal? Okay, but we are given that they are just linearly independent. Then how can we convert it into orthogonal set? That is something that is given by Gram-Schmidt's process. Okay, I'll go through the process very slowly, and we will also try to solve the example of that. So let's say you have vector w1, w2, wn given to you. These are linearly independent. Okay. Now, in order to obtain orthogonal vectors, you will take v1 as w1. Okay. So the first vector that you take is same as the first vector of this set. Okay. You take any vector as the first vector. Now, to obtain v2, what you will do is from w2, okay, you will subtract projection of the projection of w2 onto v1. So first of all, we obtained v1. Then in v2, if you want to subtract anything from w2, that is in direction of v1. Okay, that is v1 square into v1. Okay, we'll subtract this thing. Okay, we will obtain v2. Now, in order to get v3, again what we will do is v3 w3 minus projection of w3 onto v1 minus projection of w3 onto v2. Okay, so whatever after this we get w1, w, which is v1, v2, v3, this we will obtain, whatever we would get, these would be our orthogonal vectors, and they are also linearly independent. Okay, so this is a formula that is given. So vk is nothing but wk minus till k minus 1. So right now we are summing till v1, then we went to v2, that is k minus 1, projection multiplied by that vector itself. Okay, Let's try to solve an example on this. Okay, then I think this would be more clear. What I said, that we'll take V1 as W1. So our V1 became 1 0 1 0. Okay, what is V2? V2 is W2 minus W2 inner product with V1 divided by V1 square into V1. Let's do this. What is my W2? This is 1 1 1 1. Okay, minus of. Now what is W2 comma V1? W2 is 1 1 1 1 and my V1 is 1 0 1 0. So what is 1 0 1 0 dot 1 1 1 1? This is 1 into 1 is 1 plus 0 plus 1 plus 0. This is 2 divided by norm of V1 square. What is norm of V1 square? This is 1 plus 1 square, that is 2, right? And this is 1 0 1 0. What we will get is this is 1, so we'll get 0 1 0 1. This is our V2. Okay. What is V3? Is W3 minus W3 comma V1 by V1 square into V1 minus W3 comma V2 V2 square into V2, right? Again, we can write this thing. Now W3 is 0 1 2 1. 0 1 2 1. Okay. Now what we do is, if you take its dot product with 1 0 1 0, what do you obtain? 2. Right? You can do this. Then we have norm of V1 square, that is again 2, times V1, that is 1 0 1 0. And now we have the second one from here. This is V2, right? So if you take V3 with V2, this is 0 times 0 is 0, right? And then you have 1 times 1 is 1, then again 0, and 1 times 1 as 1. So this is again 2. And if you have norm of V2, that is also 2, and then you have 0 1 0 1. So this thing you obtain as minus 1. So 0 minus 1 minus 0 is minus 1. This is 1 minus 0 minus 1 is 0. 2 minus 1, 0 is 1. And the last one is again 1 minus 1 is 0. So what you have obtained? You have obtained V1 is equal to 1 0 1 0, V2 is equal to 0 1 0 1, and V3 is equal to minus 1 comma 0 comma 1 comma 0. Now if this is what you obtained as your orthogonal vectors. So whatever was span of whatever was span of W1, W2, W3, that is same as your span of V1, V2, V3 now. Okay. So this is something that is called as Gram-Schmidt's orthogonalization. And you can easily check that if you take the dot product of these two, this would be 1 times 0 plus 0 times 1, 0, 0, everything. And this would be 0 if you take any combination, if you take V1, V2 or V2, V3. This is equal to V3, V1. This is always 0. You can check whatever you obtained are in fact orthogonal. I had one more example, but we don't have time left. You can try this example, and or the book that I'm referring to for this chapter is your Fredberg's book. You can solve examples from there also, so that you gain confidence. One more thing, that we obtained orthogonal vectors. Okay, like here it is mentioned, if somebody asks you to obtain orthonormal vectors rather than orthogonal, then what you will do is you will first obtain orthogonal vectors. Okay, the same way we did, we will obtain orthogonal vectors, and then we will normalize those vectors. Okay, so for example, if you have v1, then you will make v1 new, let's say, as v1 by norm of v1. You will do something like this after you have obtained the orthogonal vectors. If you have v2, you can do v2 by norm of v2, and you call it new. Okay. Okay. Any doubt in this, or you want to ask anything about whatever was discussed today? Okay. So I'll end the recording.